All right. Good afternoon, dear members of the Dissertation Council, dear colleagues. Today is February 3rd, 2026. A meeting of the Dissertation Council under Al-Farabi Kazakh National University being held with a quorum present for the group of specialties and educational programs 60, 06, 04, 00 Physics, 60, 07, 23, 00 Technical Physics, 60, 06, 11, 00 Physics and Astronomy, 60, 07, 10, 00 Material Science and Technology of New Materials, 60, 07, 17, 00 Thermal Power Engineering, 80, 07, 108 Electric Power Engineering, 80, 01, 501 Physics, 60, 07, 32, 00 Standardization and Certification, 80, 05, 309 Nuclear Medicine, 60, 07, 1900 Radio Engineering, Electronics and Telecommunication. All 9 members are present and participating in the Dissertation Council meeting according to the list, including 4 permanent members, 3 temporary members, and 2 reviewers. So the quorum is confirmed. So let me announce the attendance list. Boshkar Kvantayev, Chairman, PhD, Professor. Kunduz Turyahanovna, Scientific Secretary, Candidate of Physical and Mathematical Sciences, Associate Professor. Kalgash Chumagulova, Deputy Chair, Doctor of Physical and Mathematical Sciences, Professor. Saltanat Buligenova, Member of the Dissertation Council, the Permanent Member, Doctor of Physical and Mathematical Sciences, Professor. Next, Tomasz Achrimyuk, PhD, Professor, Head of the Energy Conversion Department, Polish Academy of Sciences, Gdansk, Poland. He is our first reviewer. Second reviewer, Mateusz Vnukowski, PhD, Assistant Professor, Wrocław University of Science and Technology, Wrocław, Poland. Ongar Bulbul, temporary member of the Dissertation Council, PhD, Associate Professor, Kazakh National Technical Research University, named after Sarpayev, Almaty, Kazakhstan. Jakub Mularski, temporary member of the Dissertation Council, PhD, Assistant Professor, Wrocław University of Science and Technology, Wrocław, Poland. Prichodko Nikolai, temporary member of the Dissertation Council, Doctor of Chemical Sciences, Associate Professor, Head of the Laboratory, Flame Synthesis and Carbon Nanomaterials, Institute of Combustion Products, Almaty, Kazakhstan. So there is proposal to start the meeting of the Dissertation Council. Are there any objections?
No.
Okay. So I hereby declare the meeting of the Dissertation Council open. So on today's agenda, the defense of the dissertation work by Orunbasar M.N, entitled Energy and Ecological Efficiency of Plasma Coal Burners, Numerical Simulations and Experiment, submitted for the degree of Doctor of Philosophy, PhD, in the educational program AD 07106, Thermal Power Engineering. The work was carried out at the Department of Thermal Physics and Technical Physics at Al-Farabi Kazakh National University. So scientific advisors, domestic scientific advisor, Mr. Vladimir, Doctor of Technical Sciences, Professor of Al-Farabi, Kazakh National University. Foreign Scientific Advisor, Slavenskaya Nadezhda, PhD, Senior Researcher at the Technical University of Munich, Germany. So official reviewers are present. Dissertation is submitted for defense for the first time. All members of the dissertation council have received the materials related to this dissertation work. Are there any comments or questions regarding the agenda?
No.
No? Okay, no comments. Then agenda is approved. So in order to present the personal file of the dissertation candidate, applicant, the floor is given to the scientific secretary of the dissertation council, Mundus Turikhanova.
Thank you. Dear members of the dissertation council, allow me to familiarize you with the materials related to the dissertation of М.Н. Орынбасар. First document is the application address to the chairman of board director of Al-Farabi Kazakh National University for the acceptance and the submission of dissertation work for defense. Second document is dissertation work printed and on electronic media. Third document, information about the doctoral candidate М.Н. Орынбасар, which was born on the January 26 in 1996 in Chimkent, Kazakhstan. In 2013, he enrolled at Al-Farabi Kazakh National University, graduating in 2017 with a degree in thermal power engineering in baccalaureate degree. From the 2018 and 2020, he completed a master program in environmental protection at the University of Rolniczy, Krakow, Poland. From 2020 to 2023, he completed his doctoral studies in thermal power engineering at Al-Farabi Kazakh National University. Currently, he is a postdoctoral researcher at Al-Farabi Kazakh National University. First document, certified personal information sheet of Al-Farabi Kazakh National University's employee. This document, certified copy of transcript in 3 languages, confirming completion of the doctoral program. Next document, references from the domestic and the foreign scientific supervisors certified at their respective places of their work. Next document, extract from the protocol of the department meeting containing a positive assessment and a recommendation for the work to be defined, approved by the member of board vice rector for the science and the innovation of Al-Farabi Kazakh National University. Reviews from the official reviewers certified at their respective places of the work. And the 9th document, certificate issued by the National Center of Scientific Technical Information for plagiarism check. And the 10th document, certificate from the Scientific Library of Al-Farabi Kazakh National University confirming submission of the dissertation and abstract. 11th document, extract from the Academic Council meeting protocol of Al-Farabi Kazakh National University approving the dissertation topic and scientific advisors. And the 12th document, extract from the order of chairman of board director of Al-Farabi Kazakh National University on submitting the dissertation for defense. 13th document, list of scientific works and the copies certified by the scientific secretary of the Faculty of Physics and Technology at Al-Farabi Kazakh National University. 14th document, conclusion of the university's local ethics committee. As a result of dissertation research, 14 publications were produced, including 7 articles in journals recommended by the Committee for Quality Assurance in the sphere of science and higher education of the Minister of Science and Higher Education of the Republic of Kazakhstan. 1 article in the journal with non-impact factor index in the International Databases Web of Science, Clarity Analytics and the Scopes. 5 papers presented at the international scientific conferences, and 1 publication in the collective monograph recommended by the Academic Council of Institute of Combustion Programs of the National Academy of the Sciences of the Republic of Kazakhstan. The materials submitted by М.Н. Орынбасар comply with the approved rules for preparing dissertations for defense, established by the Committee of Quality Assurance in the sphere of science and higher education of the Ministry of Science and Higher Education of the Republic of Kazakhstan. The dissertation is approved for defense.
Okay, thank you, Dr. Kunduz. Dear colleagues, are there questions regarding the file of М.Н., CV of М.Н.? No questions? Okay. So if there are no questions, the floor is given to Marjan Orunbasar to present his results. So time limit is minutes. So please proceed.
Thank you. Hello, dear members. My name is Marjan Orunbasar. My dissertation topic is about energy and ecological efficiency of plasma coal burners, numerical simulation, and experiment. In the educational program, thermal power engineering, my scientific consultants, domestic scientific consultant is Mr. Vladimir Efremovich, who is a doctor of technical sciences and professor at Farabi Kazakh Medical University, Almaty, Kazakhstan. And foreign scientific consultant is Slavinskaya Nadezhda Alexandrovna. She is a senior researcher, PhD, from Technical University of Munich, Germany. Relevance of the research work today: low-grade high-ash coals are used in polarized coal thermal power plants in Kazakhstan and CIS countries. However, direct combustion of such fuels in existing combustion devices presents significant problems. The widely used technology for heating boilers and stabilizing the combustion of a polarized coal flare in thermal power plants is ineffective from an environmental, energy, and economic point of view. Plasma coal burner is a promising technology in the field of thermal power engineering that uses plasma to ignite and stabilize the combustion of polarized coal. This totally eliminates the need for additional highly reactive fuels such as heavy oil and natural gas, and etc. The plasma technology is based on electrothermal fuel preparation for combustion, which uses electric arc plasma to heat in the air mixture to a temperature at which volatile substances are released and partial gasification of coke residues occurs. Consequently, PCB, plasma coal burner, produces highly reactive dual component fuel. We call it HRDF, from the original solid fuel consisting of combustible gas, which is combined with carbon monoxide and hydrogen and coke residue. As a result, at the outlet of plasma coal burner, the HRDF ignites intensively due to mixing with secondary air in the boiler furnace. Experimental studies on plasma coal burners have confirmed that high ash solid fuel can be ignited and burned stably using PCB technology. The aim of dissertation is to assess the environmental and energy efficiency of using plasma coal burner at polarized coal thermal power plants. To achieve these goals, it was necessary to solve the next following tasks. The first task is to perform thermodynamic and kinetic modeling of the products formed during the electrothermochemical preparation of equibustus coal or low rank high ash fuel for combustion, using the Terra and Plasmic internal software packages, respectively, in order to obtain a highly reactive dual component fuel at the outlet of PCB. To conduct experimental studies of PIC's processes, plasma ignition and combustion stabilization within the burner balloon. And the third aim is to determine the optimal parameters, ensuring the efficient progress of plasma ignition and partial gasification processes of polarized coal fuel within the balloon of PCB. The object of this study is plasma coal burners. The subject of the research is the process of electrothermochemical preparation for combustion of equibustus coal in a PCB. Our research methods based on numerical analysis were performed using Terra and Plasmic internal software packages, which are designed for thermodynamic and kinetic calculations, respectively. To analyze the results, experimental studies were conducted using a PCB and compared with the numerical results. The scientific novelty of the work lies in obtaining the following new results. The first novelty is numerical simulation. was performed for the first time, confirming the possibility of producing highly reactive dual component fuel from exhausted coal using a PCB. The second novelty is experimental data were obtained for the first time, confirming the formation of synthesis gas with a total concentration 37.1% during the plasma ignition and partial gasification processes for exhausted coal in a chamber. The third novelty is optimization of plasma ignition and partial gasification processes of exhausted coal, and the value of burner was carried out and optimal parameters were determined. Statements for defense. The first statement is electrothermal chemical preparation of polarized low-grade exhausted coal for combustion enables the production of a HRDF comprising combustible gases and coke residue with elevated concentrations of CO, carbon monoxide 26.5% and hydrogen 15.2% during rapid ignition at the outlet of PCB. The highly reactive dual component fuel at the outlet of the experimental setup with a specific calorific value, 12,550 kilojoule per kilogram, ensures stable and intensive ignition when mixed with the secondary air. The optimal parameters of the PCB are an average mass temperature of 1880 Kelvin, pressure of 0.1 megapascal, plasma tone power of 60 kilowatts, with its length of 3 meters and diameter is 0.15 meters. Technical characteristics, composition and fractional composition of low-grade exhausted coal. Here is the technical characteristics: moisture content, volatile matter, fixed carbon ash content, which is very high. It's about 40%. The data from the certificate of I gave the reference there, and the chemical composition combined with mineral components and organic components. There is exhausted coal fractional composition. There is particle diameters from 10 microns to 120 microns. The average diameter was 60 microns. Main windows of the interface of software packages Terra and Plasma Kinter. The first main interface window of the Terra software, which used for thermodynamic modeling. The second is the main interface window for kinetic modeling, the software package Plasma Kinter. Here at the first equation with the entropy, the maximum of entropy shows it's the basic of Terra program, and the second chemical reaction with the metallic oxide and carbon, and gave metal and carbon monoxide. Here are results of the thermodynamic analysis. The first figure is the dependence of the concentration of gases, gas phase on the temperature, and we can see that the synthesis gas concentration rapidly growing till 1000 Kelvin, and then it's more stable. And there the maximum concentration of synthesis gas was 57.6%. It's at the temperature 1880 Kelvin with the atmospheric pressure. The second next figure number 4, the dependence of the concentration of condensed phase on the temperature. Here is the main chemical element is carbon, condensed carbon. We can see it's in the figure number 5 too. At temperature 1700 Kelvin, we can see the the concentration of condensed carbon is decreasing. It's because of converting to the carbon monoxide. Carbon monoxide. There are combustible components in the figure number 5, synthesis gas and the methane, and also carbon, condensed carbon. Here are also the main key factor of PICS process. It's the degree of carbon gasification, the level concentration of carbon gasification. We find by this equation, by this formula, the difference of concentrations of initial concentration and final concentration of carbon divided by initial carbon concentration multiplied by 100%. We can see there the degree of carbon gasification. It's the partial. It's about 60%. And here is the temperature dependence of specific energy consumption on PICS. Here, at the temperature 1880 Kelvin, at the optimal temperature, the specific energy consumption is 1.18 kilowatts hour per kilogram. And the formula for specific energy consumption, it's from the initial and equilibrium states of enthalpies, the difference. The adopted model for describing the for kinetic calculations, and here is the kinetic parameters of reactions for volatile substances. The adopted model is described using differential equations. Here is the equations number 6 and 7. It's the momentum conservation for the gases. The next equation is for cold particles, and this is for energy conservation for gas and energy conservation for cold particles. And here is the cold rate, the air mixture, the mass of air mixture, and the mass of plasma forming gas. The heat of here is for volatile substances. This is Arrhenius equation. Here are results of kinetic modeling of PICS process from the plasma heater program. The change in the composition of the gas along the length of PCB for 3 plasmatron powers 40, 60, and 80 kilowatts. So the initial temperature is 300 Kelvin. The length is 3 meters. Diameter is 0.15 meter, and comparison of power levels 40, 60, 80 kilowatts showed that for 60 kilowatt, the maximum syngas concentration at the burner outlet, the concentration was 41.7%, while the minimum CO2 dioxide of carbon dioxide concentration was 1.43%. Therefore, under these geometric conditions, a burner power of 60 kilowatt is considered optimal. Here is the change in the temperature of cold fractions at the plasmatron powers. That's the figure number 10, change in gas temperature at the plasmatron power of 40, 60, and 80 kilowatts. Changing the velocity for cold fractions. That's changing gas velocity at the plasmatron power. Here is experimental setup for research work. Experimental plasma cold burner. It's combined with the chamber, mobilized section, plasma torch, cold dust hopper, dust dispenser, centrifugal fan for air supply, and confuser diffuser, fan drive motor to drive this mechanism. The scheme of exhaust gases extraction from plasma cold burner. The main key here is this is a high temperature filter with replaceable filler made of superfine basalt fiber, and the syringe for gas extraction and closer. Here are pictures of the HRDF flame at the outlet of the plasma cold burner during the batch tests, experimental studies, scientific traineeship, breaks inside the metal cylindrical burner, general view of PCB. Here is the comparison of experimental and numerical values. We can see we did two experiments for it, and high reactive dual component fuel, temperature, temperatures, and synthesis gases and CO2 gases, and the degree of carbon gasification. The discrepancy level shows 23%, which is good agreements, less than 25%. 25% is good. Good for complex combustion processes. There's conclusion. My scientific publications. Here are three scientific publications. It will be in. They are in Q2 journal with high impact factor. They are in the process. The first scientific publication it's already published, and the two scientific publications are in the process. Here's the act on use. Certificates, premiership certificates.
So, okay, thank you. So the presentation is over. So dear colleagues, do you have questions, comments? Our colleagues online. Reviews. Okay, can you use the house initiative?
Мынандай сұрақтарым бар бірнеше. Біріншісі плазмалық әсердің көмірдің термохимиялық түрленуіне ықпалы қандай? Одан кейін және кинетикалық моделдер жасадыңыз ғой, сол жерде қандай бастапқы және шекаралық тақтар қолданыңыз? Одан кейін көмірдің гасификациялану дәрежесінің өзгеруінде жалынның тұрақтылығы қалай әсер етті? Классификациялау жасаған кезде. Одан кейін осы жеткен нәтижеңіз түсіп қазандықтарда қолданыла ма болашақта?
Соны сұраққа жауап беріп берейін. Так, ол жерде бізде плазменный угольная горелка, бұл полиугольная тепловой электростанцияда қолданылады. Бұл негізі бұндай технология Қытайда және де Ресей мемлекеттерінде қолданыста. Енді қолданылады Қазақстанда жасаймыз деп ойлаймын. Сосын плазма кемпер программасы бойынша бізде негізгі бізде так колорейт, угольный расход, расход воздуха және де толықтай экибастуз көмірінің характеристикаларын қойдық. Термохимиялық түрлендіру Так сұрақты кішкене толық қойып жүрсіз бе?
Плазмалық әсердің көмірдің темір химиялық түрлерінің ықпалы бар ма?
Химиялық құрамы қалай өзгереді?
Химиялық құрамы. Так, бұл жерде негізгі көмір бізде көміртектен тұрады. Бұл жерде бұл плазмалық әсер болған кезде бұл жерде сол бізде синтез газ бөліп шығарамыз. Плазманың әсерінен сол толық жанбаудың әсерінен СО деген газ бөлінеді. СО және сутек газдар.
Кинетикалық модельдерден қандай бастапқыш шарттар, шекаралық шарттар қолданыңыз?
Бұл жерде біз негізгі плазма кинтерм программасында сол негізгі характеристикасы бойынша экобастуз көмірінің характеристикасын, сосын расходтарын солар бойынша қойдық, сол бойынша программа жұмыс жасайды.
Спасибо за презентацию. У меня такой вопрос. Вот понятное дело, доказано уже, но это не первая ваша, наверное, защита, не ваша, а до вас тоже защита. Все-таки перспектива, эффективность чувствуется, но понятно. Тем более у нас экибастуз юга, 40% дорог, примерно. Вот перспектива в Казахстане, когда-нибудь будет, и в чем причина? И где это, в общем-то, применяется на сегодняшний день, вот эта вот система? А почему в Казахстане она применялась или сейчас не применяется? Причина в чем? Как вы думаете? Вот это ваша роль.
Да, очень хороший вопрос. Да, вообще, как я сказал, то есть, получается, вот эти плазменные угольные горелки, они применяются уже в Китае и в России. Как бы в Казахстане вот только пока на лабораторном уровне, я так думаю, это в будущем как бы у нас все равно без угля, уголь это как бы дает нам стабильную энергию. В будущем все равно у нас тепловых электростанций очень много. И надеюсь, это будет модернизация, да. Ну, пока что вот газ есть, газ используется пока.
А зачем все-таки вот не проходит эта система? В чем причина основная? Или вы это, собственно, понятно, что это не ваш вопрос, но в принципе, раз вы этим исследуете, вы, наверное, мечтаете, чтобы эта система внедрилась в Казахстане, я так понимаю, чтобы была реальность практического применения в нашей республике.
Экономическая.
Ну, то есть причину особо не задумывались, или это все-таки какие-то
экономическая, да, экономическая причина, как бы модернизация на именно на плазменную угольную горелку, потому что это требует больших вложений, да, больших инвестиций.
То есть понятно, что причина вот опять в экономике, да?
Да.
Хорошо, спасибо.
All right. Other questions, comments, dear colleagues?
Yes, I have some questions. Can I?
Please.
Yeah. First of all, thank you for invitation me, scientific boards, and I prepared some questions from our candidate. The first one is connected to this fundamental limitation of describing plasma ignition using equilibrium thermodynamics. It means there is some fundamental limitation in describing such a plasma ignition.
Thank you for the question. Yes, the limitations, like fundamental limitations, maybe it's because of these active ions by plasma, chemical reactions with the electron, like active ions.
Okay, I have the second question connected to first one. I'm thinking about can we speak on some optimal degree of non-equilibrium in plasma ignition? Let's say some optimum of degree of non-equilibrium from the viewpoint of ignition and stability and energy as efficiency.
For optimal plasma ignition, I think the main key factors that which affecting their cold rates and air rates, also that plasma power.
Okay, and then the last my question in this time, let's. That's very interesting in your PhD. They are using this software, this plasma Kinter. My question is possible to use this software to let's say investigate combustion of biomass or RDF? It's possible from point of view. How was your experience?
Thank you for the question. In my opinion, yeah, it's we have other we used this plasma Kinter program not only for plasma cold burners, but also we have published with the plasma classification processes of wasty, I think biomass and RDF. They were also the program, habitual program plasma Kinter will be good for plasma classification and biomass and pyrolysis processes. Yeah.
Thank you very much.
Okay, thank you.
Can I,
Yes, please.
on the figure 8, is concentrations of different gases are presented, and at first we can see that concentration of gases are less than 1%. It's about 1%, and then на выходе it's concentration grows. Why?
Can you repeat
So the first
picture?
picture and all picture, we can see that concentration of H2, CO, CO2, H2O, all concentration is about 1 or less. Концентрация меньше единицы, да? А на выходе из трубы, да, это плазмотруб, концентрация резко вырастает. За счет чего там? 40%, да, суммарно.
Да, если посмотреть вот эти картинки, получается, вот первая картинка показывает на 40 киловатт, там 60 киловатт и 80 киловатт, да? Это можно посмотреть, потому что у нас длина плазменной угольной горелки 3 метра, то есть это 3 метра, это показывает на выходе, да, плазменной угольной горелки.
Ну,
получается...
Проценты от чего? Если начальная концентрация была там.
Да, получается, при процессе плазменного воспламенения там газифицируется у нас углерод, да? Конденсирование углерода газифицируется и переходит в фазу газа, да? Газовую фазу СО.
А изначально углерод не указан, значит, концентрация, да?
Ну, то есть это тут газовая фаза, да? Тут написано, что композиция, то есть состав газовой фазы. А можно посмотреть это концентрацию, вот если посмотреть, ну, получается, есть рисунки еще конденсированной фазы, да? Где там углерод конденсирован. Тут все чисто вот газовая фаза.
То есть углерод здесь не указан, но он преобразуется
Ну,
в газ.
сейчас
и-
это я могу показать вам.
А водород?
Вот здесь можно посмотреть.
А водород откуда берется?
Водород это как бы там присутствует пар. Пар это также вот плазменное воспламенение переходит вот газ, водород. Там можно посмотреть, вот 60 киловатт на выходе, там СО2 газа, концентрация маленькая, и как бы синтез газ увеличивается максимально.
Ну, хорошо, значит, твердый углерод преобразуется в синтез газ. А сколько процент твердого углерода тогда преобразуется в синтез?
Сколько процентов?
Или часть полностью?
Там получается именно можно посмотреть вот степень газификации, да, где там partial gasification, частичная газификация, да. Там где-то вот в экспериментах у нас получились вот 60,5, 53,8, на American Population 57,6%.
Половина, да?
Половину.
Other questions?
Yes, I do have one more question. My name is Mateusz Wnukowski. I'm one of the reviewers. Thank you for inviting me to this event. Can you confirm that you hear me?
Yeah.
Yes, we hear.
Okay. Okay, Majdan, I have one question. Like if we could scroll to the figure 9, the one that shows temperatures. Like there is a okay, if we look at figure, okay, maybe we can focus on figure 10. There is a one thing that seems no, okay, now it's okay. Okay, I think it's a bit different than it was in the dissertation. Cause I think in the dissertation the temperature profiles didn't fix the powers. Now it seems okay, cause the temperature increases with the power. Okay, so my question is not valid anymore, cause I see there was a change and an improvement, and now it seems intuitive. So okay, my point was that in the dissertation, I think the figures might have been mismatched with the description, and the highest power was associated with the lowest temperature. Now it's the opposite, so now it seems perfectly aligned with what intuitively we can observe. So thank you.
All right, thank you. Other questions? Jakub Mularski, please.
Yeah, thank you very much for inviting me as well for this dissertation.
You are welcome.
Yeah, can you hear me?
Yes.
Okay. Can you go to figure 3?
Yes.
Yeah. So basically, if I'm correct, so those concentrations which you obtained with respect to the temperature of the process are obtained from the numerical modeling, or are they taken directly from the experiment?
These results came from the thermodynamic modeling by computer program Terra numerical simulation results.
Okay. And have you, for example, maybe considered, like, you did carry out the experiment, but my point is whether, for example, you did the experiment for example, for different temperatures, and for example, have you checked the agreement between model and the result for a high range of temperatures?
other temperatures. So, can you repeat the question, please?
Yeah, so basically here you have the concentration of the components of the PICS process. So in the experiment, for instance, for the when you had also here the table, so the comparison between the result and the and the numerical part, right? As far as my memory serves.
Yes, at the end we have the temperature comparison also. It's about at the outlet of a plasma cold burner. It's for two experiments, so the highly reactive fuel component fuel. It's also for the calculation. This calculation temperature came from the plasma kinter program.
So those are the main, let's say, components that you did include in the analysis as for the comparison between model and the experiment.
Sorry?
So those components as carbon monoxide, hydrogen, carbon dioxide, and nitrogen, and the degree of conversion are the main, let's say, parameters that you analyzed as a comparison between model and the results.
Yes.
Okay, okay. Okay, thank you.
Thank you. So do we still have questions, comments? Yes, okay.
And in your statement, Pangjan, you give that the optimal temperature 1880, yeah? And could you physical explanation?
Third statement, right?
Yeah, so statement. The optimal temperature, yeah, could you explain in physical?
Which one?
Optimal temperature.
1880
Yeah.
Kelvin.
Physical explanation.
Ah.
Could you give-
Here, so the average mass temperature it's 1880 Kelvin. It's because of that's there is high concentration of syngas, synthesis gas, carbon monoxide, and plus hydrogen. At this temperature, we have high concentration. So that's why we used as an optimal parameter, optimal temperature.
Okay. So I have also a few questions. The first one is related to your software. Is it publicly available? Is it open?
Computer programs, right? Software.
Yeah, the one that you use for your simulations.
Yes, we have a lot of applications with this computer programs, Plasma Kinter and Terra. It gave that we have a verification.
No, are they publicly available? Those software.
Not so much, I think, in my opinion.
Okay. Have you compared your results with the ones in the literature? Because so far I see only your results.
Literature is it, right?
Yes, comparison with other works in the literature.
You have comparison with other results.
With other results. Here, yes, calculations. The calculation. That there is like distinguished numbers. So I used these numbers, but we had other numbers. That's not correct.
No, my question. I'm sure that there are people who conducted similar research in Germany, I don't know, somewhere where people use coal instead of gas, or like in your case. So have you compared your results with those results in the literature? I see here only experimental, I mean, simulation, plus you have numerical analysis.
Yes, I did it in the publications. In the publications, I did some results about which some data from the other literature review. I compared with them, but they are in publications.
Mm. So the last question is related to your act of use. Where did you use your act?
Yes, act on use. It's for technical solutions for Kuznetsovsk, Gresk, the city Kuznetsovsk, Republic of Buryatia, Russian Federation.
Russian Federation.
It's
Okay. So, so do you still have questions?
Yes, I have one. Could you say some words about the practical application of our results in the power plant? You mentioned that in this act I see before.
sorry, practical.
Yeah. Could you say some word about practical application of our burner in a real power plant?
Yes, so in practical applications, mostly they are used in China and Russia, and we have in laboratory in laboratory states, but it's also published in other conferences.
Do you have some idea about how about a long time of such devices, living time? Because this is quite sensitive from the temperature. But do you know there some do you meet some let's say articles and reports in which they say, for example, our installation works 10, 20 years, something like that?
So yes, we think that in Kazakhstan we are also maybe we will do also the modernization of for this plasma coal burner in the future, and yeah, we have many of articles for this plasma coal burner, plasma coal burners, and it's optimizing day by day, and in the future it will grow in advanced level.
Okay, thank you very much.
About duration of your setup. How long does it last?
Duration of plasma coal burner.
Yes.
Duration is about 30 years. Yeah, maybe it's 30 years.
Around 30 years.
Around 30 years.
Okay. Other questions? I think yeah, it's enough. So we have plenty of questions. So the next floor is given to the domestic scientific advisor, Doctor of Technical Sciences, Professor Mr. Lev Vladimir.
Thank you. Dear Chair, dear colleagues, I would like to read my review of the dissertation by М.Н. and Ecological efficiency of plasma coal burners numerical simulation and experiment submitted for the degree of Doctor of Philosophy in the educational program 8D07106 thermal power engineering. Currently, the primary fuel used in pulverized coal thermal power plants in Kazakhstan and other post-Soviet countries consists of low-grade, high-ash coal extracted through open pit mining. These coal are characterized by high ash content and low volatile matter yield. Direct combustion of such low-quality fuels in existing furnace system presents significant challenges due to difficulties in ignition and complete burnout, as well as increased emissions of harmful pollutants into the atmosphere, including ash, NOx, and SOx. The dissertation by Orынбасar is dedicated to optimizing an innovative, environmentally friendly and efficient plasma technology for the use of plasma coal burner, as well as conducting numerical and experimental studies of the processes of plasma ignition and combustion stabilization of low reactivity exposed coal users in burner. To achieve the state objectives, the candidate employed mathematical modeling of plasma ignition and combustion software and kinetic modelers plasma burner to investigate the plasma ignition process. The practical value of the research lies in determining the calculated optimal parameters of the plasma system for plasma ignition processes, as well as identifying general patterns in the distribution of temperature, velocity, and concentration of products resulting from the electrothermochemical preparation of fuel for combustion along the length of plasma coal burner. The results of the dissertation can be applied at thermal power plant and boiler facilities operated on pulverized coal fuel to optimize the performance of plasma coal burners. It is important to note that the dissertation was carried out in accordance with the approved research plan of the Ministry of Science and Higher Education of the Republic of Kazakhstan and within the framework of grant funding scientific research under the following projects: production of energy, gas, and natural inorganic material through plasma gasification of carbon-containing waste, development and testing of technologies for new functional materials using plasma chemical and self-propagation high-temperature synthesis processes, and environmental and energy efficiency of plasma technology, numerical modeling and experiment in 2023-2026 years. During the course of the research, Orынбасar M.Н. has proved himself to be a competent young scientist, capable of independently solving complex scientific and technical problems. I believe that the scientific results obtained in this work fully meet the requirements for a PhD dissertation as a candidate M.Н. Orınbasar undoubtedly deserves to be awarded the degree of Doctor of Philosophy in Education for 2023. six thermal power engineers, certificates, doctor of technical science, professor of the Kazakh National University. Thank you very much. И от себя я вот хотел сейчас новейшее кое-что добавить, что тогда еще не было, когда я тоже специал. Вот выступление нашего президента, такая вот на последнем крутая, вы все читали, изучали, он там отдельно выделил вот энергетику, что он, как и президент Трамп, любит уголь. То есть сейчас казахстанская энергетика – это объективная вот реальность, я считаю, выступление нашего президента было. У нас 75% до сих пор вырабатывается энергии на угле в Казахстане. Вот как бы мы ни стараемся, вот смотрите, 7% всего возобновляемое, ветер, солнце, 10% это гидроэнергия, тоже возобновляемая, но уже все реки перекрыты, зарегулированы. И резерв, вот газа нет своего в Казахстане подведенного в станциях. Мы только на вот сейчас узбекский газ к нам идет на перестройку ТЭЦ-2. Узбекский газ. Они захотят узбеки, откроют, захотят, прикроют. Уже так не раз было. Поэтому вот президент наш обратил внимание, что нужно использовать наш уголь, которого запасы у нас на 300 лет, по нынешнему уровню его использования. И только для этого необходимо разработать энергетически эффективные и экологически приемлемые технологии использования современные. И вот я считаю, вот та технология, которая посвятил исследованию, которой посвятил свою работу Макжан, она как раз вот в этом ряду находится. И вот вопросы очень хорошие были вот профессора Приходько. Вот почему в Казахстане, да, мы живем, угля полно, там, вот, она разработана, эта технология в Казахстане была. Мной лично, в газе, энергетике. То есть наша технология, покупать не надо, уголь свой. Почему она не разрабатывается? Она не внедряется. Потому что считает, что лучше брать, вот, пусть купить у узбеков газ, то есть экономические проблемы, и нежелание, ну вот, пусть сам Рукэнерго. Вот после Экспо 2017, где наш проект один из 29 был выставлен как прорывной, вот по вот этим безмазутной ростовке плазменной, они даже включили в государственный план еще в 2017 году. И что они сюда приезжали. Мы должны были выйти вот на вторую очередь Экибастузской ТЭС ГРЭС-2. Вот о которой тоже, кстати, такая говорил, что третий блок ставить. Мы должны на третий блок ставить вот эту технологию. В итоге там потом сменилось это руководство Рукэнерго и так далее. Какие-то бюрократические, экономические причины. Вот это мое мнение человека, который занимался этим всю жизнь. Это вот то, что я просто накипело, хотелось вот кое-что ответить на это. Ну а вот еще возвращаясь, вот почему вы думаете, польские, вот они согласились, это уникальный случай, 2 польских рецензента, вот почему? Потому что Польша угольная страна. Вот у нас в Казахстане 75% электроэнергии на угле вырабатывается, а в Польше 65%. У них уголь, у них ничего больше нет, остальное все покупное. Газ тот же и так далее, нефть. Они тоже хотят освоить эту технологию. Почему Макжан там вот работал у них, там уже будучи вот, в докторантуре, там все лето провел. Они хотели через Макжана чего-нибудь освоить нашего казахстанского для себя. Это очень приятно. Вот почему у них такие вопросы вот часто они задавали, да? Они очень интересуются всем. Мы стараемся, конечно, с ними делиться, так сказать, помогать через Макжан. Ну, нам не жалко. Что, пусть там работает, здесь у нас работает, идей хватает. И вот последнее, что я хочу сказать, вот действительно, у Макжана, вот мы беседовали до защиты с председателем насчет публикации. Да, у Макжана там в самом начале была опубликована, там, это, ну, он удовлетворял формально вот этим положению о защите PhD, так, Вот там в Скопус ходил, ну, низкий там 35, что ли, это был этот процентиль. Ну вот неделю назад вышло в одном из ведущих наших журналов американском, это, значит, он Plasma Science, вот этот журнал, значит, статья с участием Акжан, первый автор, там процентиль 56. Вот. Так что и сейчас вот с рецензией неделю назад пришла журнал Basis, вот, у него процентиль 72%, там тоже первый автор Макжан. То есть я хочу сказать, что он не на нисходящей вот, да, после защиты, а как бы защита это только трамплин для него, для дальнейшего его это, расцвета на нашей кафедре.
Спасибо.
Спасибо.
Хорошо. Спасибо. Okay, thank you. So now the floor is given to the scientific secretary of the dissertation council, to Dr. Dus, to announce the review of the foreign scientific advisor, PhD, senior researcher at the Technical University of Munich, Slavinskaya Nadezhda.
Thank you. Let me introduce the review of foreign advisor. Review of dissertation entitled Energy and Ecological Efficiency of Plasma Cold Burns. Numerical simulation and the experiment was submitted by Marjan Ornbasar for the degree of Doctor of Philosophy, PhD, in the educational program AD 07106 Thermal Power Engineering. In his dissertation, Mr. Marjan Ornbasar addresses the challenges of optimizing of plasma coal burner and developing an environmentally friendly, energy efficient plasma ignition and the combustion stabilization technology for low reactivity aqueous cool. Results of this work have been published in 8 peer-reviewed journals, including engineering physics and thermophysics and aeromechanics and Gareni e Plasmia. Throughout the project, Mr. Ornbasar demonstrated the ability to plan and execute complex experimental combines, develop and apply advanced numerical tools, and interpret results critically. His simulated results showed good agreement with experimental data, confirming the validity of his approach. He has proven himself to be competent young scientist capable of the independent work on challenging some energy problems. Recommendation. In view of scientific results achieved and their practical relevance, I consider Mr. Marjan Ornbasar fully qualified for the degree of Doctor of Philosophy, PhD, in Thermal Power Engineering, AD 07106. Senior Scientist, Doctoring, Head of NIDS Group, Nadezhda Slavinskaya, Technical University, Munich. Thank you.
Okay, thank you. Now the floor is given to the first official reviewer, PhD, head of the Energy Conversion Department, Polish Academy of Science, Tomasz Ochrimiuk. Please, you can give your review in your own words without reading. So only the last part you can just read for protocol. The rest you can. Yes.
Thank you very much.
Yeah.
What can I say? The thesis, this is good part of work. It was very well written. I read this PhD thesis with much interesting. I learned something from this thesis. It's most important for me. And I appreciate the amount of work which was conducted by PhD candidate. They performed also numerical simulation, and what is very important, such a thesis, they made and conduct his own experiment using, let's say, full scale burner. It was very impressive for me, and the results was very good. When I say about the comparison between numerical simulation and experimental, the results was quite similar. That's I read a lot of word in my review, but summarizing that, I would like to say that Mr. Magdan Ozenbar is deserving of being awarded to the academic degree of Doctor of Philosophy in the education program 8D07106 Thermal Power Engineering. It was signature by me, Tomasz Okreniuk, head of Energy Conversion Department, Polish Academy of Science. Thank you very much.
Okay, thank you. So now the floor is given to the second official reviewer, PhD assistant professor of Wrocław University of Science and Technology, Mateusz Wnukowski.
Thank you. I will allow myself to read the summarization of the review. So once again, dear chair and the members of the dissertation committee, thank you for involving me in this event. I would like to present the main conclusion of my review of the dissertation of Magdan Orynbasar entitled Energy and Ecological Efficiency of Plasma Coal Burners, Numerical Simulations and Experimented, submitted for the degree of Doctor of Philosophy in the educational program of Thermal Power Engineering. The dissertation addresses an important and practically relevant problem related to the energy and environmental efficiency of plasma coal burners used for ignition and stabilization of pulverized coal combustions and thermal power plants. The topic corresponds to priority directions of scientific and technological development of Republic of Kazakhstan and was carried out within a framework of state-funded research projects. The work focused on plasma-assisted combustion of low-grade, high-ash coal, which is widely used in Kazakhstan and poses significant technological and environmental challenges. The research combines numerical modeling and experimental studies, which allows the author to investigate electrothermochemical fuel preparation, partial gasification, and ignition process under conditions close to industrial practice. The numerical part of the dissertation is based on well-established and mature tools, namely the Terra and Plasma Kinterm software packages. The modeling results are logically presented and generally well justified. The experimental investigation complements the numerical analysis and demonstrates reasonable agreement with the simulation results, which strengthen the credibility of the main conclusions. At the same time, I identified several shortcomings, in particular the energy and ecological efficiency of plasma coal burners, although stated in the title, is addressed rather superficially and is not defined or quantified in a sufficient systematic manner. The structure of the dissertation could be improved and some sections are repeated. Certain fragments are not strictly connected to the main narrative, and the experimental results would benefit from being presented in a separate, dedicated chapter. Additionally, the original version of the dissertation contained an insufficient description of the experimental methodology. Following my comments, the author submitted a revised version that provides additional methodological details and answers a few of my questions. Although I believe that the description could be expanded further, I also believe that now it provides acceptable level for ensuring the reliability and repeatability of the presented experimental results. Therefore, it can be stated that all the questions have been answered and all the recommendations have been taken into account, and no crucial remarks regarding the dissertation have been left without response. Regarding scientific novelty, the work does not introduce fundamentally new concepts. However, its novelty lies in the adaptation and validation of plasma-based ignition technologies for specific coal properties and regulatory conditions of Kazakhstan, which enhance the practical relevance of existing scientific knowledge. The main provisions submitted for defense are generally proven, or rather proven, and not trivial, and have a high level of applicability. They are supported by publications in peer-reviewed scientific journals. The dissertation has a theoretical value, particularly in improving the understanding of gasification and ignition process in plasma coal burners, and also demonstrates practical significance as the obtained results were applied to a real industrial boiler. Despite the noted limitation, such as the lack of recent international literature, limited ecological and economic comparison with alternative ignition technologies, and the absence of uncertainty and sensitivity analysis, the overall scientific level of the work is satisfactory. In conclusion, taking into account the relevance of the topic, the achieved results, the revision made in response to the reviewer comments, and the overall completeness of the dissertation with the requirements of the Committee of Science and Higher Education of the Republic of Kazakhstan, I conclude that the dissertation meets the formal criteria for awarding the degree of Doctor of Philosophy. Therefore, I support awarding Majdan Orınbasar the academic degree of Doctor of Philosophy in the educational program of Thermal and Power Energy Engineering. Thank you for your attention.
Okay, thank you very much for this detailed review. So, dear colleagues, we have heard the opinions of all the official reviewers. Now, let me open the floor for discussion. So, who wants to give speech? I mean, in support of Majdan?
Ну тут, в общем-то, прекрасно все понятно, потому что вот Владимир Ефимович тут обрисовал структуру. Действительно, Казахстану повезло, что есть такие у нас люди, которые вот занимаются этой технологией. Другой мир, конечно, технологию из-под тишка может и забрать, как Китай говорит, забрали спокойно, тихо. А у нас все это, пожалуйста, люди есть, платите деньги, они вам внедрят это дело, обследуют их, как правило, вот интересуются там другие страны. Конечно, это перспективная технология. Конечно, есть у нас альтернатива, это понятно, атомная энергетика. Эта перспектива еще на впереди, она к этому подойдет. Но сейчас Казахстан, как известно, в основном угольная страна. Поэтому в любом случае теплоэлектростанции, я сам, у меня специальность теплоэлектрической станции, я работал, еще будучи студентом на этих станциях, типа КЭЦ-1 и прочее, я понимаю эти проблемы, поэтому я вижу, что все-таки это перспектива, вот то, что у нас Орынбасар Макжан, вот он, как говорится, молодой и перспективный в плане этого исследования, в плане внедрения, я думаю, доведут до ума в Казахстане. Я, конечно, очень рад, что вот послушал его, так сказать, его содержание его диссертации. Она действительно уникальна, даже в том плане моделирования. Из нас очень мало кто занимается моделированием. Практически специалистов раз-два обчелся. Вот у нас тоже у Славянской это Мадир, а Конвертауна у нее тоже интересовалась, изучалась. Ну, в принципе, очень сложно идет моделирование. Но моделирование эффективно чем? Тем, что все-таки не используя экспериментальные данные, можно меньше экономический вклад и получить результаты те же самые, когда уже есть наработки экспериментальные. Это вот сделано у Макжана, естественно, он сравнил, показал, да, эффект есть, оно однозначно дает положительный результат. Экономика, я думаю, тоже положительна, потому что если просто брать и смотреть, как энергетический вклад, вот розжиг плазмы, вот это все, создание этой установки, это колоссальные тоже затраты требуют. Но если сравнивать с тем количеством, которое потом не сжигается, используется для других химических целей, да, тот же мазут, тот же там, другие газ и прочее, конечно, эффект большой получается. Поэтому я все-таки буду голосовать за. Ну и, в общем-то, я призываю всех тоже проголосовать положительно за то, чтобы присвоить степень доктора философии PhD Орынбасару Макжану Баумлы по образовательной программе 8D07-106 теплоэнергетика. Спасибо.
Спасибо большое. Thank you. So, our online colleagues, would you like to speak some words in support of Majdan? We can ask Jakub Mularski.
Thank you. So, you mean by summarizing, right?
Yes.
Yeah. So, as for the presentation, I find it novel. As for the results, so the theoretical, both practical and theoretical investigation, and I find it that the thesis should be overall proceeded, and the doctoral degree should be awarded. Thank you.
Yeah, thank you. So,
Мағжан Орынбасар, учителем по образовательной программе типа энергетика бакалавриат. У нас такой вот, у нас на кафедре, а магистратуру он учился в Польше. И приехал сюда, продолжил свою учебу в докторантуре, сейчас по специальности типа энергетики. Был доклад, хорошо ответил всех вопросов, выиграл Мағжан научный проект Жасгалом, сейчас в данный момент работает, исследовательски работаю с руководителем Владимиром Ефремовичем. Только что вот Владимир Ефремович сказал, что действительно продвижение по публикации уже идет по спортсам, там по центрам 56-70. Желаем удачи, я прошу вас поддержать Мағжан по образовательной программе 8Т 07 1006 типа энергетики голосовать за ученых, за утверждение степени только отлично.
Я тоже поддерживаю. Очень такое выступление было мы сегодня заслушали. Интересный доклад. Тематика очень актуальная, поэтому полностью поддерживаю.
Еще, уважаемые коллеги, вот Мағжан на 3 языках отвечает: на казахском, на английском, на русском, да? Спасибо.
okay, thank you very much. So now we should follow the next step. So now the final words are given to the candidate. Please, Mағжан, you can express your own, say, opinion. Conclude.
Thank you for your members of Dissertation Council, for your energy, for your time. It's my gratitude, sincere gratitude to my supervisor for his constant support, answering willingness to answer for all my questions at any time. It's my thank you. Also, I would like to thank you to my family who will support and for their understanding. Thank you.
Okay, thank you. So now we conclude our discussion and we move on the next stage of the council meeting. So for the secret ballot procedure, the floor is given to the scientific secretary, Dr. Kunduz.
Thank you so much. Dear members of Dissertation Council, for the secret ballot procedure, a link of online voting platform has been sent to your email. Please check your email and cast your vote, please. Now I'm sending it. Okay.
Right, dear colleagues. So for the announcement of the secret ballot results, the floor is given to the scientific secretary, Dr. Kunduz.
Thank you.
Person.
Okay, thank you. Do you see my screen?
Yes, yes.
Okay, thank you. Please, let's introduce the results of secret ballot. To award the degree of Doctor Philosophy PhD, we've got 9 votes, and to refer to the dissertation for revision 0, to refer the dissertation for the defense 0, to revise the award of the degree of Philosophy PhD, Doctor of Philosophy PhD 0. The results are certified by the electronic Excel form. Do you see here? And the diagram form. Thank you.
Okay, thank you. So, within the framework of the dissertation council at Al-Farabi Kazakh National University for the group of specialties and educational programs, physics, technical physics, physics and astronomy, material science and technology of new materials, thermal power engineering, electric power engineering, physics, standardization and certification, nuclear medicine, radio engineering, electronics and telecommunication. So Marjan Orunbasar is awarded the academic degree of Doctor of Philosophy PhD in the educational program AG07106 Thermal Power Engineering. So congratulations. Now, dear colleagues, we have now only last stage. According to the regulations, we need to adopt the council's conclusion on the dissertation of Marjan Orunbasar. So the draft of conclusion and the classification attributes of the dissertation have been distributed to all the council members. So are there any comments or suggestions regarding this conclusion?
No.
Okay. So it's proposed to adopt this conclusion as a basis. So hereby the meeting of the dissertation council of the defense of doctoral dissertation of Marjan Orunbasar is officially announced closed. So thank you for your participation. Thank you for your support. See you next time. Bye bye.
Yeah. Thank you so much.
Thank you. Congratulations,
much.
Majdan.
Thank you.
Thank you.
Thank you very much
Congratulations.
for your active participation. Okay. Bye bye.
Bye.